everyone. Yeah, sure.
So, good evening, everyone. Welcome to the last day of the Limit Online Camp. This is the last stop of the entire Limit Online Camp. Today, we have with us Professor Prasit Bhattacharya. He did his PhD in mathematics from the Indiana University at Bloomington. His main interests are in algebraic topology, homotopy theory, classical geometry, and he's currently a professor at the Department of Mathematical Sciences in New Mexico State University. Today, he'll be speaking on the topic when homotopy meets algebra. Over to you, sir.
Thank you very much for the invitation. It's a great pleasure to talk in this particular seminar series or online series. Um, so the topic that I chose today is when homotopy meets algebra. Um, I just want to gauge my audience a little bit before I start talking about it. Um, so this topic is about how algebraic methods seeped into homotopy theory, or how homotopy theory embraced algebraic methods and what comes out of it. This is a very active area of research and used in many other areas. It's a modern way of thinking, but to give this talk, I need my audience to have some basic knowledge about algebra, like group theory, etc. And they may or may not have to see topology or topological spaces. So I want to know if all of you are familiar with group theory. Um, I don't know how to, if there is a thumbs up or anything, that should be good enough.
Yeah, thumbs up should be great. These are mostly first year students, first year university students, so they should be familiar with group theory.
Okay, so let me then start there. So let's see how homotopy meets algebra. So let's talk about some basic objects in algebra. The things that you have seen are probably, group, rings, and I don't know if you have seen this, but today I'm going to talk about it a little bit, which are called monoids. Um, so, monoids are groups without the inverses. For instance, natural numbers have an addition, but you cannot have the negative numbers, so you do not have inverses of any given number. So somehow having an inverse is nice because it makes you look at more algebraic properties. You can do more manipulation, multiply by inverse, and do cancellation. But that's an additional axiom that I don't want to assume every time. That will save us some time. Although I can always expand my talk to basic objects like groups. So I'm going to start with the definition of group. So what you might have already seen is that a group is a set G with a unit and a multiplication which satisfies some conditions like unitality, associativity, and existence of inverse. So one way to understand all of these things is to think of, instead of thinking of in terms of sets and elements, we will think everything in terms of maps. So where I'm going to talk about a unit is it's a map from a one-point set to your set, which you are denoting by G. And then you are going to think of multiplication as a binary operation, meaning a map from G cross G to G. That means your input is two elements of G, and output is one element of your group G. So now we have some conditions, and these conditions can also be written in terms of arrows. I want to particularly do this exercise um, because it will allow us to connect to different things. Um, Goes without saying, by the way, like anyone should just feel free to interrupt me at any point. I would strongly encourage. Um, okay, so let's see what unitality means in terms of diagram. So 1 dot g is equal to g is g dot 1. So way to write this is, um, let's see. So I'm going to have a diagram something like this. So I have a 1 point cross g, and then there is this map including um, uh, using the unit map, which is e, I guess. So I want e here, and then I can also go the other way. So g cross a point, um, uh, 1 cross e, and then you're going to use the multiplication to land in g. But look, uh, a point across a set G is canonically isomorphic to G. So use that isomorphism, and you want to say that this diagram commutes. Um, Commutativity of this diagram is equivalent to writing this equation. And similarly, you can talk about associativity. You can say, so I have G cross G, and what I can do, I can multiply the first two factors. So I can do dot cross the identity, and I land in G cross G. And then I multiply again to go to G. But that's not the only way to go from G cross G cross G to G. There is another way, which is you can multiply these two factors on the tail. So you can do 1 cross the multiplication, and then you multiply the factors. And if you ask this diagram to commute, this is precisely talking about associativity. Because if I start with G1, G2, G3, if I go around like this, I get G1. First, I multiply G1 and G2, then I multiply with G3. Whereas if I go around that side, I get G1 multiplied with G2, G3. And commutativity of this diagram is saying that, oh, well, these two are equal. Similarly, you can write down a diagram for inverse. Um, so inverse would be, you can think of inverse as a map from G to G, maybe a bijection in this case. And it should have the property that if I take an element G and apply the diagonal map, and then I apply the inverse bijection cross the identity, land in G cross G, and then I multiply. So way to think about this is, let's see, I have an element G here, then I go to diagonal, so it will go to G comma G, and then it will go to G inverse, what I'm calling G inverse, and then I multiply, so this will be G inverse dot G, but it should be the unit, right? By G inverse G. So that means what I gotta do is I gotta say that this thing is factoring. So this is the collapse map. So send all the elements of group G to a point, and then you use the unit map. So that's here. So it factors through this point why the or factors through the unit map, and that's your existence of inverse diagram. Any questions so far? Okay, good. So what I'm gonna do is I'm gonna for my talk, if I remove this axiom or remove the existence, then I'm gonna say this is monoid and the rest remains as it is. Um, okay, so I took a very basic object, and which is group, and in the world of groups, um, you study morphisms, or morphisms are group homomorphisms. Um, the best way to think about this is in terms of category theory. If you have seen category theory, please put a thumbs up. Okay, yeah, thumbs down if you haven't. Okay, that's also good. I can, okay, some up, some down. Okay, great. All right, thank you. Okay, so way to think about this is don't worry about any category theory or anything. Just think of, I have this world where all the things that I'm going to study are groups, and the kind of maps between groups that I'm interested. You, I mean, they are after all set, but you cannot just take any map. You take the maps that preserves the structure, which are the group homomorphism. So if you really think about it, uh, uh, if I have a map from G to H, these are the kind of group homomorphisms that. So the group homomorphism should satisfy, um, f of G1 dot G2, where this multiplication here is taking place in the domain group, which is G in this case, and should equal should equal f of G1 dot f of G2, where the second multiplication on the right hand side is taking place in H. Um, this is also actually a commutative diagram if you think about it. So a morphism F is a set map which satisfies, um, so so of course there is G, there is a map F to H, but then there is this multiplication. And here I can apply F cross F to H cross H. And then I multiply in H, and this diagram must commute. And this is precisely recording this equation. Okay. Um, so this is some basic object in group, and we are going to talk about how it influences or how it is perceived in topology. So let me introduce what we mean by topological space. So the mathematicians soon figured out that just working with sets is not enough to capture the kind of things that we learn. For example, in analysis, we look at real numbers, and we have a notion of continuous functions. And to really talk about continuous functions in general, you need to have what is called a topological space. What are they? Well, they are actually a set with some additional structures, which is the additional data of open sets. So rigorously, a collection of open sets are collection of subsets of your set X. So the way I'm writing it is that the collection of all open set is a subset of the power set of X, such that it is um, closed under arbitrary union, and finite intersection. For instance, if you take the real line, you can give it a topology using open intervals. So your open sets are open intervals and arbitrary union of open intervals. Um, so if you take a bunch of open intervals and if you intersect them, you will get um, things that are disjoint union of open intervals. But you will only get that if you do finite intersection. If you do infinite intersection, then you might end up with a point, which is not an interval. So with this topology, you can talk about continuous functions. Continuous functions are those which are those maps such that the inverse image of an open set is open. This is like the abstractification of the basic notion of continuous map that you have seen in analysis, for instance. Um, a continuous map is where you draw a graph without lifting a pencil from your paper. So this notion captures um, continuity. Um, and one of the things that we are going to learn today is what is the notion of homotopy. Okay, another survey. How many of you have uh, seen homotopy before? You can also put a thumbs down if you haven't seen. I want to know how many thumbs down are there. Okay, all right, good. Okay, I'm gonna not assume anything. Any questions so far? So, any questions on topological space and notion of continuity? Everyone good with that? Okay. So, homotopy. So what happens is, if you want to study for for real lines or like for things that you study in analysis in low dimensions, you can do explicit calculations. For an arbitrary topological space, if you try to study all continuous functions, then you're going to have issues because it's going to be too large and too much to handle. So then we say that, okay, you know what, we will have a notion of homotopy. So what is homotopy? Well, we say that two maps are roughly the same or homotopic if over a time unit we can deform one map to the other. That means you were at f, but over a time interval you can probably change your map little by little continuously, and then get into G, and then effectively f and G, although looks very different map, but effectively they are same map if you study things up to homotopy. So it's a little bit of relaxation, but the thing is you then um, have a smaller collection to worry about. So way to do this rigorously is we define the notion of homotopy to be um, um, to be a continuous map from your domain space X cross the unit interval to Y, such that at time 0 you are F and at time 1 you are G. Um, and at any given time you have a function which is interpolating between F and G. So then you define the set of homotopy class to be set of all continuous maps up to homotopy, meaning that you introduce an equivalence relation using homotopy. F is equivalent to G if they're homotopy, and quotient out by that equivalence relation, you get a set which is collection of maps. And this set might be much smaller than collection of all functions from x to y. In some cases, if all maps are homotopic to each other from x to y, then you know that this set might in fact contain just one point. I wonder if you have seen homotopy, the some examples of homotopy before. Maybe you have seen something like a winding number. You know, um, so if you think about a collection of maps from, let's do an example here. Um, Example, you know, so if I look at maps from S1 to S1, um, um, so there are, how many maps are there from circle to circle up to homotopy? Circle is pretty easy to understand. At least we can picture it. Um, any guesses? There are many maps from S1 to S1, but up to homotopy, there are actually integer many maps, one for each integer, and this number is called the winding number. So it's the number of times your map has wrapped around the other circle. So for instance, it could wrap around once, that's one, and it could wrap around twice, that's two. It could wrap around maybe 10 times, that's 10. Or if you go in the negative direction, which is, let's say, clockwise direction, then you have negative winding numbers. So by convention, these things come up in physics, complex analysis, and other places. So there are integer many maps um, uh, from S1 to S1. So now you will notice a small thing that I want to elaborate. Here, I wrote down that this is a set of homotopy classes, right? So I should really give you a set. But I have not given you a set here. I have given you something more than a set. I have given you a group, in fact. Integers form a group under addition. So the question is, when uh, can this set be upgraded to a group or a monoid? So that's the question that I want to ask. Okay, I have taken two topological space, x and y, took all the continuous functions from x to y and modded out by the homotopy relation. Can it form a group? Can it be a group? Okay, any questions, or is the question clear that we are trying to address here? Because this is the question that's going to lead us to the main topic, and let us see um, how homotopy is going to meet algebra. So this is the prime question of this talk. Okay, so let me maybe rephrase this question, or if um, so we are studying um, homotopy class of maps from x to y. The question that I'm just asking is not that when this becomes a group randomly, I'm asking a slightly deeper question. The deeper question is, what should y satisfy so that for any x, the homotopy class of maps from x to y is a monoid or a group? Not only that, I'm also asking a little more, that when if f is a continuous map from, let's say, x1 to x2, um, then it will uh, introduce a map, um, it will introduce a map f upper star in the backward direction from x, homotopy class of maps from x2 to y to homotopy class of maps from x1 to y. Why in the backward direction? Well, because if I have a map from, let's say, x2 to y, uh, call this alpha, then what I can do, I can precompose by f and produce a map from um, from um, from x1 to y. So the map really goes in the backward direction. It is given by precomposition by f. And so now, if y is such that this is a group, that's not enough. I want this map to be a group homomorphism, or a homomorphism of monoid. So I want to address this question. Why is y? Well, when will y will have such a property that these two questions will have an affirmative answer? All right. I'll pause here to see if there is any questions. Okay, looks
There
good.
are questions.
Yeah, question, please.
No, no. I was just telling you that there are no questions, I think, at this point. Yeah,
Okay,
sorry.
okay, sounds good. Okay, so if you have seen category theory, so one way to look at it, or I'm not going to use category, but I'm going to use the world. So, um, so if you look at the world of topological space, and you see a little op out there. This op out there is because you see the reversal of arrows, right? Like if I have a map, from x1 to x2, you get a map from homotopy class of maps, from so it changes the direction basically. So that's why there is this up. So so if I take world of topological spaces where maps are continuous maps, and apply this construction where I take a topological space X, and consider all possible continuous maps into Y and take its homotopy class, I get a set. I get a set. And not only that, for any map from x1 to x2, I get a map of set in the backward direction, hence this up. But I am asking for conditions on y such that I can satisfy some lifting problem. So basically, I want to understand, when does it lift here and when does it lift here in this world. That's what I'm asking. And for today's talk, let me just not focus on this part. Let me just address that. Okay. So actually, the answer is not complicated, because we have already done the homework at the beginning of this talk. What y should satisfy in order to in order for it to satisfy this condition? The answer is that y should be equipped with a unit and a multiplication. Note that this has to be continuous maps because y is a topological space, such that you have this diagram commuting where um, where you take the unit to define the horizontal maps, and these are the canonical isomorphisms, and this is the multiplication, and it must satisfy some associativity diagram. And because we are asking, because we are taking homotopy class of maps, we want these diagrams not to commute on the nose, but up to homotopy. Okay, so now what do I mean? Meaning that this diagram is not exactly commuting on the nose, but there is a homotopy between the maps that we get if we go along one edge of the square versus when we go along the other edge of the square. So let's see what it means rigorously. Rigorously, it means that I have a homotopy H which is going to be a map from y cross y cross y cross the unit interval to y, such that at 0, this is going to be mu composed with mu cross 1, and at 1, this is going to be mu composed with 1 cross mu. So basically, over a period of time, you can deform this composition to that composition. And these kind of spaces are called H spaces. Any questions?
Yeah, I have one question.
Yes.
Are these necessary as well? These conditions, like
This
for
condition,
this
yes,
set to be say a monoid, these conditions have to be there, is it?
these conditions has to be there. Yes, exactly. So let's look at that a little bit. So let's jump into it. Let's see how. So what does this unit map gives me? Let's ask. And what does this multiplication maps gives me? So let's look at homotopy class of maps from um, x into y. Okay. So now I have a unit map which is, and let me call y0 to be the image of this point. So within this there is a constant map at y0. So it sends every point in x to y0. This will be the unit of the monoid, and of a multiplication which is going to be defined as follows. So I need to give you a pairing like this. So let's say I have a map alpha and a map beta, which are both maps from x into y. So, and I'm going to define what is alpha star beta, which is going to be the following composition. So you're going to take X, you're going to use the diagonal map to go into X cross X, then you're going to do alpha cross beta to land in Y cross Y, and then you need the multiplication to get back here. And this is how you define, and you can show that this is an associative monoid using the conditions. But your question is slightly different. You're asking, okay, suppose we know this is associative monoid. Not only that, if I have a map from x1 to x2, I get a set map from x2y to x1y, and we know that this is going to be always a monoid homomorphism, then do we know that y has to satisfy the given property? Is this forced on us? And the answer is yes. I'll leave that as an exercise. A way to see this is you can put some canonical inputs for x and y. For x, like for example, you can put the map y itself, or you can put the map y cross y, and play around and see what you get. So okay, let's move on. So I'm addressing, what I'm noticing here is that if I consider the world of H space, it's actually much bigger. It includes all the traditional monoids that you know. In fact, traditional monoids have things commuting up to nose. But here you have things up to homotopy. So if it commutes up to nose, of course it commutes up to homotopy, but not vice versa. So, and you are allowed to have interesting topology on your monoid. So this is strictly bigger. So it allows you to study much more interesting mathematical objects. And monoid sits inside the world of groups, or actually groups sits inside the world of monoids, because those are those monoids with inverses. Similarly, there is a notion called group-like H space. Groups sit inside that, and so you can see that this is going to be the inclusion of different worlds. They sit like that. So let me discuss an example of an H space which is not a strict monoid, which comes from topology.
Can
And
you just once mention what you mean by H space? Like, what is an object in H space?
an object in H space is a topological space which is equipped with continuous maps such as this unit map from a point and a multiplication map from y cross y to y, which satisfies such that these diagrams commute up to homotopy.
Okay, thank you.
Okay, so that is what H space is. And the point of H space is that any H space will make sure that homotopy class of maps from X into Y is not just a set, it's a group. And moreover, whenever you have a continuous map from X2 to Y, X1 to X2, you will have a set map like this, which is going to be actually a map of group or map of monoid. Map of group if it is a group like H space, something that I don't want to get into today, just because it's an additional condition and I don't want to write all of them down every time when I'm trying to communicate some deeper philosophy. that might be a burden for us. Okay, so let's look at an example of an H space, which is not a strict monoid. For instance, loop space or based loop space. So this is usually denoted by omega of x. So suppose you have x with a base point x0, a prescribed point x0, then you can consider a set of all loops starting at x0 and ending at x0. So these are called based loop space. So if you collect all these functions from s1 into x, you can actually give this a topology. So this function set is not just a set, it's a space. It's a topological space with a designated open set derived out of open sets of S1 and open sets of X. The technical term is compact open topology. So for any function space, you can give some topology called the compact open topology, which makes it into a topological space. Just assume there is a topology. The precise definition doesn't matter for us. So now in this thing, you can define the unit map. So I need let me make some space here. So of course, a unit map should be a map from a point to the function space of S1 into X. So that means basically what it means is like I'm picking up a very specific loop in this loop space to be the unit, and that unit I pick to be the constant loop at the base point x0. So things, a loop, a map from S1 to S1 where you just stay at x0. That's your unit. And the multiplication is given by concatenation. What do I mean by concatenation? If I have one loop and if I have another loop, I can think of this as a joint loop where I don't consider the fact that so at the halfway point. So basically, okay, let me make it rigorous. So one way of looking at S1 is, you can think of this as unit interval 0, 1 with 1 glued with 0, right? You take a unit interval and glue 1 with 0 and you get a circle. So what you're going to do, if you have one loop L1, you squeeze it between 0 and half, you you change its speed, and then from half to 1, you do L2. So okay, so that's what I mean by concatenation. And you will see that this is actually giving you an H-space structure, except here that the associativity is not strict, because if you are concatenating 3 loop, you are allowed to concatenate in 2 different ways. First, you concatenate the first 2, then you concatenate it with the third, or first you concatenate the last 2 and then you concatenate with the first. So the difference will lie in the fact that if you look at the unit interval 0, 1, then you will notice in the first case, you're using, in the end, you're using 1/4 interval for the loop A and B, first 2 loops, and then you are adjusting the third loop in the space in the unit interval, half the unit interval, the second half. Whereas here its parameterized slightly different. Like the first one takes half the time to loop around using A, and then for B you have 1/4 time, and for C also you have 1/4 time. So these two are strictly speaking not the same map from S1 to X. In other words, these are not the same loops. However, you can always have a homotopy over a period of time. You can use the fact that you can deform, you can produce a continuous map, um, uh, which translates 1/4 interval to half interval here, and then this one remains one as it is, and this one is compressed to 1/4. So if you consider such a homotopy, then what it's going to give you is that um, you have a commutative diagram well up to homotopy, which is, I'm just giving you the idea, not getting into the rigor. Um, but these are all very fun exercises to write down explicit maps and see how it plays out. This diagram commutes up to homotopy. Okay, that's great. So let me tell you something, um, some things about this loop space. So pi 0, or the zeroth homotopy group of any space X, is the path components of your space X. So in particular, if you are looking at pi 0 of loop of X, then you're looking at path components of loop of X. So that is in the best scenario, that is set of all maps from S0. S0 is just 2 points. S0 is the boundary of one disk being the unit interval, is the set of homotopy class of maps from S0 into loop of X. Okay, so basically, S0 is 2 points, and you have loop of X, which is a space. So base point always has to go to base point, and the other point can go anywhere. But if you are considering up to homotopy, then you basically, the homotopy is giving you paths of the other point. So this is precisely the path components of loops of X. So now you can think of loop of X as functions from S1 to X, and turns out that there is something called loop suspension. There is an adjunction which allows you to push. I don't know if you have seen this for sets. Let me tell you the kind of idea I'm going to use. So on sets, I don't know if you have noticed this, that if you take set of all maps from X cross Y into Z, let me not write this notation. Let me say all functions from X cross Y into Z. This is in bijective correspondence from functions from X to functions from Y to Z. It's actually canonically a bijection. So basically, if I have a map here, alpha from X cross Y to Z, then I have to give you a map here. So what I'm going to do, so this alpha, so this bijection, let me call this pi. So pi alpha should be a map from X to function space. So pi alpha of X should be a function from Y to Z. So I have to tell you what pi alpha of X evaluated at Y is, and that's just alpha of X comma Y. and you can define the negative, uh, the inverse of this map. So the point is that you can trade the function space for Cartesian product on the other side. Similarly, you can do something in topology where the product structure is called smash product. I don't want to get into that, but the upshot is that if you smash anything with S0, you get the same space back. And the point is, under this adjunction, you can see that path components of loop of X is same as homotopy class of maps from S1 into X, which is often called the fundamental group of X. So fundamental group of X is always a group because loop of X is an H space. And therefore, when you consider fundamental group of anything, it's actually a group. You know, I started off by saying that pi1 or the homotopy class of maps from S1 into S1 is forming a group. Um, and um, and this is where it comes from, because this at the end of the day is the number of components of loop of S1, or in other words, it's the set of maps from based maps from S0 into loop of S1, and this has to be a group. Anyway, there are consequences of such structures. The reason why we ask such a question, not because for the sake of mathematics, but because additional structure allows you to detect more stuff or answer more interesting questions. So a very important example is the Brouwer fixed point theorem. I'm not going to go into the proof. That's going to be done in some topology lecture at some point. But what I'm going to say is that Brouwer fixed point theorem says that if I have um, um, a map um, if I have a map from a 2-disk to S1, it will always have a fixed point. Okay, any continuous map has a fixed point. And this really requires the fact that the fundamental group of S1 is actually a group. So if it weren't a group, this proof is going to fail. And it tells you something beautiful about geometry. Okay, any questions? Now I'm going to change gear. Now I'm going to not be flippy floppy and not be up to homotopy, and enter what is called homotopical algebra. So I'm going to talk about, so I have roughly half an hour, I guess. So higher homotopy. So, you know, earlier I said, okay, this diagram commutes up to homotopy for an H space. I am now going to be rigorous about this homotopy. So I'm going to think of this homotopy as a path in the function space from the threefold Cartesian product of X to X. So so at 0, this is, I'm going to call this, I'm going to call the multiplication the twofold multiplication. So I'm going to mark them by mu2. And I'm going to call this homotopy mu3. So mu3 at 0 is mu2 composed with mu2 cross 1 and mu3 at 1 is mu2 composed with 1 cross mu2. Okay, everyone good with that? There is a reason why I chose the notation mu3 instead of h that I was using for homotopy previously. So the way I want you to think is that uh, that this homotopy is not just a homotopy. This is a three-array operation, meaning that it takes three inputs and produces one output. And there is not just one three-array operation. There is a unit interval worth of three-array operation, a space of three-array operations, which is interpolating between your two favorite ones, which are not necessarily equal. Another way to look at this is in terms of tree diagrams. You can think of this mu3 as, a map on unit interval where on the boundary maps, these are determined by mu2. So let me just point that out. So these two are determined by mu2. And mu3 is like a homotopy between these two. So you can think of this as an average. So in terms of tree, I denote it by a tree with no internal edges, as if these internal edges. So here, this is telling you exactly how you are multiplying things. So if I write down A, B, and C, you know that you are first multiplying A and B and then multiplying C. Whereas if I write down A, B, and C here, you see that first you're multiplying B and C and then you're multiplying by A on the left. But if I write down A, B, and C here, I don't see which one I'm doing first, and that is kind of encoding the one cell of your unit interval. Any questions here? So the whole point of this discussion is that I'm going to think of this homotopy as a space of three-array operations. Okay, that's fun. So let's move on. Now let's ask. Okay, let's not forget. Let's not be up to homotopy. Let's ask, what is fourfold associativity? Um, so let me start with a question. If I give you a mu2, a twofold multiplication, how many different maps can you construct? How many different four-array operations can you construct out of this? Let's think about this. So I have given you, I know how to multiply two things. So you can do something like A dot B dot C dot D, or you can do A dot BC dot D. You can do different stuff. You can do AB dot BC. So how many different things can you do? Well, any answers? Let's see who is good at counting here. Okay, I'm going to give you the answer. The answer is actually 5. And if you think about this, the best way to encode them is using tree diagram. So this multiplication is given by a tree which looks like this: A, B, C, D. This one looks like that. So actually there are 5 of them, and they can be they can be written like, let's see. So one, so you have that tree. Oh, I actually have the pentagon here. Okay. So it's the bound. You can think of this as the pentagon, the edge, the corners of this pentagon. So let me write them down. Okay, so these are the 5 vertices of the pentagon. So now let me make this a little more interesting. Um, you see that now if I have the homotopy, if things are homotopy associative, meaning that I have this mu3, then actually I can connect the vertices of this. So in other words, I can produce a map from here to function space from x4 x, and I can do it on the boundary of the pentagon using mu3. In fact, I will have T diagram to describe how I'm going to use mu3. So here I'm going to have, so you see that the tree that I'm going to draw here is going to be one that you can obtain from either here or there by collapsing one of the edges. So for instance, here you can collapse this one, and for here you can collapse that one. So that means that once I have a mu3, I can define a map on this boundary. So here I can have that. Okay, so I can define it now on the boundary of the pentagon. But the question is, can I fill up the pentagon? Can I fill up the pentagon? So this pentagon, this is actually, I'm going to denote this pentagon with the interior as K4. I'm going to talk to you about what these are in a bit. So what happens is that given mu2 and mu3, I can define, we have a map from boundary of this pentagon, which I'm going to denote by K4 for whatever reason I'm calling it K4, to function space from fourfold Cartesian product of x into x. And K4 is the boundary of, a boundary of K4 is of course sitting inside K4. And the question is, can I fill up this pentagon? Can I fill it up? Look, this was exactly the kind of question that we asked for the threefold associativity, which is, I could define the boundary of this unit interval in this case, which I'm going to call K3. And The question was, can we fill it up? And the answer was no. It's an additional data which we are calling mu3. So likewise, here, if we can lift it up, that's going to be mu4. So this was an observation due to Stashev. And you realize that the once you have defined homotopy up to associativity, the coherence, homotopy coherence among the fourfold associativity is not guaranteed. There is something to be filled in. So if you can fill in, you call it a fourfold associative H space. And if you can't, then you are only a threefold associative. So this led to a refinement of the definition of H space and the notion of higher associativity. So let me do this for fivefold. Okay, for fivefold, things get a little crazy. So there is a polytope. These are K4, K5, and all these things are called Stashev polytopes. So you can look up. This is the fifth Stashev polytope. So this looks like, it contains. There are pictures online you can probably look up. It contains bunch of. It's made out of bunch of squares and pentagons and so on. It's a very interesting polytope. And so given mu2, mu3, mu4, we can define a map from boundary of K5 to the function space, a fivefold Cartesian product of x into x. However, we cannot really fill in, and if I can, mu5, then we call x an A5 H space, meaning fivefold associative. And if you can fill in all the way, then you call this A infinity. That is in the homotopical world, that's the closest you can get to being strictly associative. So these polytopes are called Stashev associahedron, and in general you can define one for each n, and they are actually homeomorphic to a disk of dimension n-2 and has a very rich cellular structure. The zero cells or the vertices are given by planar rooted binary trees where every internal node has 2 leaves. So overall, you are forced to have n-2 internal nodes. And in general, if I have if I look at the K cells of this, then you have n-2 minus K. So you collapse one of the edges. And so they are in one-to-one correspondence with planar rooted, no longer binary, just trees, as seen. Like, for example, here, like the pentagon, you see that the one, here it is 4, so 4 minus 2 is 2 minus 1. So you have only one internal edge to describe the one cells. Any questions at this point?
Yeah, I have a question.
Yeah.
So you look at that space functions from like 4 Cartesian powers of x to x, that one.
Yes.
Yeah. In the compact open topology, if this is simply connected, then can we say we can fill up that pentagon?
If this function space is simply connected, then you can fill up this pentagon. Yes. So you're telling me that yes, we can fill it up when because this is S1, right? So if pi1 of function space of x to the 4x is 0, then you can fill it up. But not always you're going to have that. Similarly, in the next case, this is actually S2. So if pi2 of function space of is 0, then you can always fill it up. That means anything is null homotopy, so you can use that homotopy to develop this mu5. But it's if it is not 0, uh, uh, then you cannot really conclude anything. So to answer your question, yes, good observation, but that's a lucky case.
Thanks.
Okay, so coming back to Stasheff associahedron, you can define all these polytopes, and you can define um, an AN structure on H space as a compatible family of maps, which looks like in general mu n is going to be kn cross n to x. So by the way, if I have a function from the kth stash polytope like this, it is equivalent to giving a map like that. So I can think of this in both ways. Sorry, this is so you can by the adjunction I discussed earlier, mu k can be also thought of as a map from the kth stash of polytope cross k-fold Cartesian product of x into x. So this is sort of parameterizing k-fold k-array operations. So in algebra, you don't study higher array operations, because once you have two array and strict associativity, all the n-array operations, there is only one n-array operation. It's forced on you by the strict associativity condition. But once you loosen it, you have different options. So let me ask a question that that was a prime subject of study in these 50s, 60s, and 70s, which is that does Sn, the n-sphere, support an H-space structure? So for example, S0, let's start with zero sphere, which is the boundary of one disk being the unit interval, is plus or minus 1. You see that plus or minus 1 can be thought of as a Z mod 2. So it's not just an H space. It's in fact a strict monoid. In fact, it's a group. So S0 is just a group. How about S1? S1, S1 also has a multiplication, because you can think of this as sitting inside the complex numbers as unit length complex numbers. And so it gets a multiplication. How about S2? Can the two sphere have a multiplication? The answer is actually no. And you will study this later on in advanced topology course, why it's no. I don't want to get into the details in this talk. Now let me ask about S3. What about S3? Does it have A multiplication? Any guesses? How many of you think it's yes? Just put your thumbs up if you think yes. Okay, only one person thinks yes. Okay, a couple more. No. Okay. Good, 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 good. So actually, S3 does have a multiplication, because you can think of this as sitting inside um, the unit quaternions. So there are quaternionic multiplications. So that's on R4. Um, so these are the unit length quaternion, um, often denoted by H, um, stands for Hamiltonian. And so if you look at the unit quaternions, you see that S3 does have a multiplication. However, there is one thing that you lose, um, going from S1 to S3, is that it's no longer commutative. S1 is complex number is commutative, but the quaternionics are not commutative. Nevertheless, it's an H space. Okay, so how about um, let's see. How about S4, S5? Let's go there. So, what do you think about S4? Does it have a? Okay, somehow people are really getting into the pattern. People think no, huh? That's great. Actually, that's true. That's no. And again, this is a proof that you're going to learn in some topology course in ISI, um, in algebraic topology course if you take one. Um, how about S5? Hmm. I was not expecting that. Okay. No. How about S6? Okay. Oh, S6. Okay. S6 also people are voting no. How about S7? Now people are thinking thumbs up. Okay. Huh. Interesting that you guys have some intuition about what the real theorem is. Okay, so let me tell you some history about this. So Steenrod showed, I think in 1950, that if Sn admits an H-space structure, then N must be of the form 2 to the k minus 1. So that means that it could be S1, S3, S7. What about S15? What about S31? So any guesses for S15? What do you think? Yes or no? Thumbs up or down? Okay, down. Okay. Everyone down? No one wants to say up? Maybe you guys already know about the history that I'm about to tell. Okay, so let me tell you what happened next. So Steenrod showed this, and then Adams in 1960 sometime, or showed that um, um, only S0, S1, S3, and S7 has H space structure. But it was a little too premature to give this theorem, because there is one thing we need to be clear. Okay, up to S3 is okay. But S7, where you get this H space structure, so let's bring up S7. S7, where you look at it, is like the unit length octonions. So there is something called octonions, and that's the end of this series. So these are the unit length octonion. I mean, you can write down very precisely that, these are like, well, A0 plus I times A1 plus JKL up to A7. I don't know what should go here. Maybe just write I1 up to I7, such that they are of unit length. But octonions are not strictly associative. It's a division algebra, all right, but it's actually not strictly associative. So the multiplication that comes from octonion is not strictly associative. So it was a question. So this led to a very important question, which was open for a while. Is S7 a homotopy associative H space? So this was an open question, and it was resolved by Stashev, a student of Milner, around 1960 something, 65, I would say. The answer is no. And the way he did it is by defining this theory of Stashev, so-called Stashev polytope and obstruction theory. And he used a lot of different techniques, but he said that S7 may have an H space, but no matter what kind of, whether it comes from octonion or something else, no matter whatever kind of multiplication you want to define, it can never be associative. There is actually a topological or homotopy theoretic obstruction to this. So this is where I'm going to end my talk. But before I end, I'm going to say that the Stashev polytopes put together form a very interesting gadget called operad. And the theory of operad is currently at the forefront of many research that takes place in homotopy theory and in algebraic topology. So this was just the story, how it was developed, so by studying associativity up to homotopy. All right, I'm going to stop here.
Thank you so much, sir, for the wonderful talk. Are there any questions? Yeah, many of us had heard the story, like the partial resolution of the story, that the only possible ones were S0, S1, S3, and S7. But the fact that S7 does not work was I think it was news to people.
I see. Yes, this is a very famous story in mathematics that you only have real complex quaternion, octonian, or in case of spheres, H structures are there. But this result of Stashev is um, not quite said out loud along the fact that S7 cannot have a homotopy associative H space um, is is um, is not said out loud. Okay, so let me tell you a consequence of this. Have you all heard about projective spaces, real projective spaces? Okay, so if you have heard about real projective spaces, then you have heard about complex projective spaces as well. So you can define things like RP2, RP3, and you can keep going. You can define up to RP infinity. Similarly, you can do CP1, CP2. CP1 is just a two sphere, then you have CP2. You can go up to CP infinity. Similarly, you can also do HP1, HP2, up to HP infinity. All of these spaces exist. But with octonian, you have OP1, you have OP2, but there is no OP3. You cannot define anything beyond OP2. That's all that you're allowed. This is a consequence of this result. Okay. Any other questions?
If not, maybe I'll ask one
Yeah,
more
one
thing. Is
one
that
question.
is there any connection to parallel? Yeah. No.
Sorry. This OP3, OP4, you can't do that quotienting because it's not 4 commutative or 5 commutative, is it?
Right, because yes, exactly. Because your S7 does not have is not A3 or A4 or A5. Yeah, exactly. You cannot.
Okay, thanks.
Yes, they are related.
So if there are no more questions, we can end the talk. Thank you, sir, for the amazing talk.
Okay, you're welcome. Thank you for having me.